let's look at some examples of using the product rule. So let's find the derivative of this using the product rule. Now this is a product of polynomials, so another way we could calculate the derivative of this is just to multiply it out and then use the sum rule and product rules. So let's actually do it both ways and just check that we get the same thing. It's always kind of reassuring when there are two completely different ways to do a calculation and they give you the same thing. So let's start out using the product rule. So remember the product rule, there are lots of ways to write it, but sort of one nice schematic way to write it is like this. uv prime is u prime v plus uv prime. I'm hesitating to call this first piece, right? Often when you look it up in textbooks and things, you'll see it with f and g, so f prime g plus fg prime. And I'm hesitating to use that one this time because this function is called f. So let's call this one u and this one v. So the derivative of f is going to be u prime v plus uv prime. So derivative of u, and I'm going to write this out, but whether you need to write out this intermediate step is kind of up to you. You might not need to. So for derivative of that piece times v with no derivative, so minus 4x to the 6th plus 7x squared, plus, and then u with no derivative, so 3x to the 5th plus 2x times v with the derivative, so derivative with respect to x of minus 4x to the 6th plus 7x squared. Okay, now this first derivative, we can just use the sum rule and the power rule. So on this first piece, right, the constant multiple just moves outside the derivative, and then derivative of x to the 5th, that's 5x to the 4th, plus, and then derivative of 2x, that 2 moves outside the derivative, and the derivative of x is 1, so just 2 there. And then times this piece that doesn't have a derivative, minus 4x to the 6th plus 7x squared, plus 3x to the 5th plus 2x times, and now we need a derivative, so this minus 4 survives, or moves outside the derivative, and then derivative of x to the 6th is 6x to the 5th, plus 7 times, and derivative of x squared is 2x. Okay, so now this 3 times 5, that's 15, and this minus 4 times 6, that's negative 24, and 2 times 7, that's 14. Okay, now the derivative calculation itself is done, but remember we're going to compare this to what we get by multiplying this out and then taking the derivative. So to be able to compare those, we're going to have to multiply this stuff out and combine like terms. So in the first piece, this looks like, let's see, 15 times minus 4 is minus 60 x to the 10th, and then let's see, here's a minus 8 times x to the 6th, and then here's 15 times 7, so 105 x to the 6th, and then 2 times, so plus 14 x squared. Alright, and now for the second line here, so 3x to the 5th times minus 24, so that's going to be what, 72, negative 72 x to the 10th, and then here's an x to the 6th, so minus 48 x to the 6th, and then here's 42 x to the 6th, and then plus 28 x squared. Okay, so putting this all together, we have negative 60 x to the 10th, and then, oh, sorry, here's more x to the 10ths down here. So negative 60, negative 132 x to the 10th, and then all our x to the 6ths, here's, let's see, here's negative 6, so negative 14, so positive 91 x to the 6th, plus, and here we have 42 x squared. Okay, so that's using the product rule. Now let's try it by multiplying everything out. So if we multiply things out first, we get, so negative 12x to the 11th, and then here's 3 times, so 21x to the 7th, and here's minus 8x to the 7th, and plus 14x cubed. So this is minus 12x to the 11th plus 13x to the 7th plus 14x cubed. And now when we take the derivative of this, we get, so this 11 comes down, so negative 12 times 11 times x to the 10th plus 13 times 7 times x to the 6th plus 14 times 3 times x squared. Okay. And then negative 12 times 11 is negative negative 132 x to the 10th. Okay, things are looking good. And then 13 times 7 is 70 plus 21, 91 x to the 6th, and then 42 x squared. So, good. We must have done the arithmetic correctly because we got the same result. So, so the product rule is giving us sane results, right? It's giving us results that are correct. The point of this example is not so much that you should want to do this calculation in the first way with the product rule. I think it's pretty clear in this case that doing it the second way is actually easier. But the point is that the product rule is giving us results that are correct. And so in the future, when we have more complicated functions that aren't just polynomials, we'll be able to use the product rule sort of safe in the knowledge that it actually works. All right, let's look at a second example. So let's suppose that we have these functions f and g, and we have a table of values for f and g and its derivatives. Now, for these derivatives to exist, f and g actually have to be defined on whole open intervals, not just at individual points. So this table isn't a complete table of values, it's just a few values. But this is kind of a typical situation to be in if you're doing some sort of scientific study where you might go out into the world and gather data, and you know the data is continuous, but you only have values for your data at certain times, say. So although you only have finitely many data points, you know that in principle it's continuous, and so these rates of change should exist. All right, so in this situation, let's find the derivative of f times g at 3. Now we don't have formulas for f and g, so we can't multiply the formulas together and then take the derivative. But what we can do is, in general, we know that the derivative of f times g is f prime of x times g of x plus f of x times g prime of x. And this gives us kind of a general formula that we can use. So now we can plug in the x value 3. So if we plug in the x value 3 to this, what we get is that f times g, the derivative of f times g at 3 is f prime at 3 times g of 3 plus f of 3 times g prime of 3. And now that we have this, we can look up these values in our table of data. So f prime of 3, that's this one, minus 5. G of 3, that's this one, so times 1, plus f of 3, that's 3, and g prime of 3, that's here, 4. So this is minus 5 plus 12, so that's 7. All right, final example. Let's find a formula for the derivative of this function, 3 times x squared times k of x plus 2x, where k of x is an unknown function. So when we find a derivative for this, it's going to have k of x and possibly k prime of x in the final result, right? Because since this is an unknown function, we won't be able to actually put a formula in here for k of x. But we can still take the derivative of h. So this, right, we need to take the derivative of 3x squared times k of x plus 2x. Now remember, the derivative sees the last operation that happens. So the last operation is that stuff plus this stuff. So the derivative really sees this addition, and so we can use the corresponding derivative rule, which is, of course, the sum rule. So the sum rule says the derivative of the sum is the sum of the derivatives. So derivative of 3x squared times k of x plus the derivative of 2x. Okay. So right now we have some remaining derivatives to do. For this first one, again, this derivative sees the last operation that happens, and the last operation is multiplication right here. So we can do the product rule. And the product rule says derivative of the first piece, so derivative with respect to x of 3x squared, times the second piece with no derivative, so k of x, plus the first piece with no derivative, 3x squared, times the derivative of k of x, which is just dk dx, plus, right, now we're done with the product rule for this piece, so now we need to write down the derivative of this piece. Well, this doesn't have any k's in it. This is just a function of x, or an explicit formula involving x, so we can actually calculate this derivative completely. So it looks like it has a constant multiple, so we can move the constant multiple outside the derivative, take the derivative of the remaining stuff, which is just x, and that's going to be 1, of course. Okay, so over here, derivative of 3x squared, this constant multiple 3, we can move that outside, and then multiply by the derivative of x squared, which is 2x, times k of x plus 3x squared times dk dx. And since we don't have a formula for the function k, we can't really write a formula for dk dx, so we just have to leave it as dk dx, plus 2 times dx dx, that's 1, so 2 times 1 is 2. And at this point, we can tidy up some arithmetic here. 6x times k of x plus 3x squared dk dx plus 2. But at this point, we've done all the derivatives that we actually can do. The only derivative left is dx or dk dx, but since k is some function that we don't know, we can't write a formula for dk dx. So at this point, we're done. We've done all the calculation we can do, and so this is our formula for the derivative of h.